pay careful attention to what you're seeing in this video. It's not a tutorial and you won't be expected to do everything I show you here, although I will be trying to teach you all of these skills in the next 8 weeks as part of this course in quality control. But my intentions now are to introduce many of the spreadsheet skills that we'll be using in the course so that you know what's up ahead: making graphs, writing formulas, copying and pasting. These are some of the main skills. And in some cases you'll see that I run into pitfalls that we'll be running into together, particularly with making graphs. But on another level, I want to show you how we can use fairly simple skills to run experiments in a spreadsheet. What do I mean by experiments? What kind of experiments? Well, in the long history of science, there's always been this problem of variation in measurement, or put it another way, hitting a target. So experiments into the nature of variation now can be done in a spreadsheet by generating random numbers. I'm going to pause here for a second to point out what I'm doing. I'm entering a formula up here for random numbers that are normally distributed with a mean of 100 and a standard deviation of 10. And Control C down at the bottom showing that I'm copying that right now. And I've been copying it and pasting it. You'll see a lot of keystrokes. Control V, Control C is paste and copy. And then Control with the arrows moves the cursor across large blocks of data. And if you add a shift to that, it selects all the data that you've moved across. So just so I pasted a bunch of data into the second column, and then I selected it. Now we're looking at graphs and trying to pick a type. And the problem I'm having, I wanted to look at this histogram as it's on the right, but it only shows one series, and I want to show both the red and the blue. Here it's shown as a line graph. And now, so I'm switching back and forth between those two graph types to try and successfully just there get a histogram chart type that shows both the red and the blue, the variable A and variable B series of numbers, which are both the same formula, the normal distribution with the standard deviation of 10 and the mean of 100. And so they can be any number that fulfills the requirements of that normal distribution in both columns A and B. And now what I'm doing here in these two new columns is adding whatever number is in column A to whatever number is in column B in each row. So that's column E or in the worksheet. And then the second column, F, the new one that I'm working on, I'm subtracting whatever is in B from whatever is in column A. Once I wrote those two formulas, A plus B, A minus B, in a format that we'll learn about and do a lot of, I copied them and pasted them all the way down to the bottom row of the worksheet, which is 1,000 rows down. Because when you're doing statistics, it's often helpful to look at the way things behave with large numbers, large data sets. And so now here I'm plotting the two variables A and B, and then the difference, A minus B. But what didn't show up in this chart that should have was the other column for A plus B. And I can't explain that, and it wasn't this way last year when we used Google Spreadsheets for this course. And I started years ago using Excel, and really liked Google Sheets because it seemed so much cleaner, and the problems with this really heavy menu in Excel made Google Sheets a lot easier to teach and to work with. But I think it's true of all software. They're always changing it. I think software guys get it nearly perfect, and then they worry about what they're going to do. Job security, if they made it perfect, they'd have to do something other than work on what they've been working on. So it's always changing, and we're always having to adjust for those changes. You can see I'm still trying now to get the series called A plus B to show up on a chart. So I went through everything I did just then. I just want 4 series shown in that line graph format. And using column C as labels there, you see I just clicked on that there, turning that on and off. We got it. So this is the chart type I've been trying to get. Persistence, patience, and practice. Those are the keys to using software and computers for that matter. So before I explain what it is that I'm trying to show you here, really the point of this spreadsheet experiment, just a few more things. Control up now is going to bounce us up to the top, and I'm getting rid of that first unsuccessful chart, trying to move this one by first you have to select it and then click into it and drag it when you see the little hand. There's things that need to be done to this chart, and one is to correct the label on the vertical axis, and then to correct the label on the horizontal axis, and I want to add numbers along the bottom. So you see I just typed a 1 there. That's the first number for the bottom labels. And then I just make a formula that whatever's in the second row equals whatever's in the first row plus 1. Then I hit enter on my keyboard and I click back to that spot, hit Control C to copy it, Control Shift down to go down, and then paste it to the whole 1,000 rows, and notice it gives me the numbers from 1 to up near 1,000. And so now I'm going back into the chart. Advanced Edit gets us into the Edit dialog box or whatever that we'll be using a lot in class, and right into the top of that there's a place to put the correct title on the chart. Last year they didn't. They just said something like chart title there, and then horizontal axis and vertical axis on the axis labels. This year they've got it trying to guess what it was that you wanted for labels, and they didn't get it right. And hopefully enough people will yell about it, complain about it, that they'll change it. And it could happen any time because this software is actually online rather than in your computer, so they could make a change to it, and we might see it during class sometime. But so now right there I've entered B instead of C to expand the data to include those numbers that I just, consecutive numbers. And notice when I then said use column B as labels, I wanted them on the x-axis. It did put numbers on the x-axis, but the plots went totally haywire. So now I'm clicking back and forth because I'm assuming that clicking out and back in gives it another chance to get it right, and it did. Now the numbers on the bottom of this graph start at 0, and you see every 100 up to 900. So we've got almost 1,000 numbers plotted in 4 series here in this chart. And while I'm labeling the axes now and setting the minimum and the maximum for the scale, the span of numbers for the vertical axis, that prevents it from jumping around once I get it where I want it, because I want to put grid lines on this chart because I want to look more carefully at the variation that we see in each of these series. Basically, what are the limits of that variation? Because this will give you some idea of the standard deviation. Because when you have a lot of numbers, and we have 1,000 here roughly, they'll go out to the extremes on above and below the average. And these extremes, is if this is testing your familiarity with the normal distribution, but these extremes above and below are 3 standard deviations away from the mean. So the limits, the highest and the lowest numbers of these sets of 1,000 numbers, will span a total distance of 3 standard deviations. Am I right? No, I'm not right. The total span from above the mean to below the mean is 6 standard deviations. Because, as we just said, the extremes go from 3 standard deviations below the mean to 3 standard deviations above the mean. So a total of 6. So let's zoom into our chart and look at how this applies to our 2 data sets called variable A and variable B. We can line up the upper extreme values at about 130 units, and the lower extremes line up at about 70 units. So the difference between them is about 60 units, and this represents 6 standard deviations. So 1 standard deviation should be 10 units. And this is no surprise because we entered a value of 10 for the formula that I used to generate these 2,000 values in the first place. So this just shows that with a couple thousand values, it's not hard to estimate standard deviation just on the basis of the most extreme values that are expected to occur in the normal distribution. And that's what we've generated here, is a couple thousand values of a normal distribution. Now, randomness comes into the picture because at any particular time in the series, we cannot predict exactly what value either variable A or variable B will have. So if we go along 1,000 number pairs and add A plus B, there will be times when A and B are both above the mean, and so the sum will be kind of doubly high. Similarly, there will be times when both A and B are below the mean, and the sum will be kind of doubly low compared with the deviation for the separate values of A and B. And then for subtraction, it's kind of reversed. No matter whether the values are high or low for A and B, if they're similar to each other, the difference is close to 0, which is the average difference. And when one is above and the other is below the mean, the deviation becomes doubly positive or doubly negative, depending on whether A is greater than B or less than B. So now we have a focus on what this experiment is all about. We can see that the extent of the variation gets greater when you add 2 variables or when you subtract them. And I don't know how it looks to you, but to me the variation looks about the same for both the sum and the difference. So it's logical to ask if there's a solid mathematical relationship here, and if so, what is it? So let's estimate the standard deviation of the sums by drawing a line at the high extremes. It looks like about 242. And the low extreme values look like about 158. So the difference there, 242 minus 158, is 84, which should represent 6 standard deviations. So 84 divided by 6 is 14, and that should be 1 standard deviation. Likewise, for the differences, the high extremes line up at about 37. The lowest extremes line up around minus 49. So 37 minus a minus is 37 plus 49, which is 86. And now if that's 6 standard deviations, 86 divided by 6 is 1 standard deviation, which equals about 14.3 for the differences. So is this just a coincidence that the standard deviation for the sums is 14 and for the differences it's 14.3? If we suppose they are the same, we could average the two and get 14.15. And then maybe we should compare this average to the original standard deviation of 10 and say that the standard deviation of the sum or the difference seems to be about 1.415 times the standard deviation of the original variables themselves. Does the number 1.415 ring a bell with any of you? And our variables A and B were normally distributed. We set it up that way. Would we get that same 1.415 relationship if the variables were distributed some other way besides normal? And we could answer that question in less than a minute, probably, by only slightly changing our spreadsheet formula. So spreadsheets give us the power to do it in a few seconds. I think we'll stop here today so that I can find out a little about who you are and what you've learned so far from this video.